Hi, I am Michael from ARM. Today, Henry and me will give you a presentation of CloudHypervisor, a new choice for virtual machine monitor. CloudHypervisor is an open source project started by Intel. It is implemented in Rust language and is based on Rust VMM project. In the first half of this presentation, I will introduce the development of Rust-based virtual machine monitors and Rust VMM, the architecture of CloudHypervisor, the virtual I/O devices of it, and how it works with Kata containers. After that, I will hand over to Henry, who will continue to talk about the progress of CloudHypervisor on ARM and make a live demo to show how everything works. The first well-known virtual machine monitor written in Rust is CrosVM. It was published in April 2017 by Google. CrossVM is based on KVM. It is designed to run on Chrome OS. Later, in October the same year, Firecracker project started. In the very beginning, Firecracker was forked from CrossVM, but it became different soon because Firecracker aimed at different use case, that is, lightweight virtual machines or micro VMs. Micro VMs are used for creating multi-tenant containers and microservices. As the two projects have some functionalities and source code in common, duplicate efforts existed. The code was frequently ported from one project to the other, and much effort was used in testing and reviewing. How can this be improved? In December 2018, developers discussed the way to share the code and finally concluded to start Rust VM project. Rust VMM shared common components for making VMMs from the two projects. After that, in May 2019, Intel announced a new VMM project, CloudHypervisor, which is based on Rust VMM. Rust VMM is a collection of Rust crates. A crate is a building block in Rust, like a library in C. These crates are well designed and tested. To build a new VMM, you only need to write the least code for combining these crates and customizing. Here are some examples of the crates. Linux loader is used for loading guest kernel, and the VM memory is for managing guest memory, etc. In future, building your own virtual machine monitor should be further simplified by using VMM reference. It is a new crate of Rust VMM introduced several months ago. It is a reference implementation on top of other crates. It aims to be convenient to extend and customize. You can choose to start your own VMM by extending this reference. Here is the diagram to show the major components of CloudHypervisor stack. Let me introduce them from top bottom up and left right one by one. On top of host Linux kernel, it is Rust VMM, and on top of that, it is CloudHypervisor. CloudHypervisor is based on KVM, but it will not be the only choice in future. From the second half of this year, Microsoft joined the community and began to extend CloudHypervisor to Hyper-V. So a new crate was designed to wrap low-layer hypervisor details, that is the hypervisor create. It has the details of KVM and provide a unique interface to upper layer components. Architecture specific things are placed in ArcCrate. For ARM64, we have code handling Geek and FTT here. VMM is the core component of CloudHypervisor. I have mentioned that on top of Rust VMM, a virtual machine monitor should only contain customizing code. In CloudHypervisor, this customizing part is VMM crate. It manages devices, memory, CPUs, and interrupts of a guest VM. VM allocator is a resource management component. It is in charge of allocating and deallocating DRAM addresses and I/O addresses and IRQ numbers. The last part is devices. It contains some crates for VirtIO and vhost user devices. Ideally, the VirtIO stuff should be designed agnostic for implementations. The vision is to make it unique in Rust VMM. But now, Rust VMM haven't been ready in this part. In future, VirtIO things in CloudHypervisor should be replaced by aligned Rust VMM crates. The conventional choice for device emulation could be QEMU, but QEMU is heavy-weighted. It emulates a number of devices, including some old ones. Well, CloudHypervisor focuses on cloud workloads only. It supports a limited set of para-virtualized devices. As a VMM running in cloud computing centers, it doesn't care much about legacy devices. VirtIO is the major type of CloudHypervisor devices. So far, it has supported many VirtIO types, including VirtIO block, balloon, console, IOMMU, networking, persistent memory, random number generator, and VSOC. Some kinds of vhost user devices are available as well. This diagram depicts the workloads of VirtIO emulation in general in CloudHypervisor. VM VirtIO handles the core model of verticals. Various device types are emulated in VirtIO device crate. In VMM crate, device manager manages all the devices. The notification from VirtIO driver in guest kernel are carried by IO event FD, which are handled by equal helper handler. In the return trip, interrupt manager can inject interrupts into guest via IRQ FD. Working as a container runtime is an important use case of lightweight VM nowadays. CloudHypervisor can work with Kata containers to achieve that. Kata containers is an open source community working to build a secure container runtime with virtual machines. By using Kata, a user feels like using a container, but in fact, the workload is isolated by a VM. This way, an additional layer of defense is built. In a pure container stack, typically runC is under the runtime layer. But with Kata, it is a VM behind the runtime. In the right half of this diagram, it is where CloudHypervisor works. It serves to provide virtual machines in which Kata agent is installed. The real container workload is running in the VM. That is all the slides for me. Now I will hand over to Henry for the rest of the presentation. Thank you for watching.
Thanks, Michael, for the wonderful sharing. From here, I'm going to talk about the CloudHypervisor on ARM. Currently, our contribution for the ARC64 platform can be divided into three parts. The first one is enabling CloudHypervisor on the ARC64 platform, where we implemented the guest VM memory layout on specific registers and devices. We also created a Rust foreign function interface for the libfdt library to implement the flattened device tree. This device tree will be used in booting the VM. Our second contribution is the ARC64 test infrastructure. This part firstly includes the enablement of the development container, as every development and test script is executed in the container. After the CloudHypervisor was enabled on ARM, we then added the ARC64 specific checks as well as the unit and integration test to the community CI. Based on this, our last key contribution to the community was about some feature enablement, including the VM snapshot and restore on ARM. Details about these contributions will be discussed in the next few slides. This slide shows the design of the ARC64 guest memory layout. One of the most important functions of this layout is to provide memory sections to allocate each kind of devices, and in each section, devices are allocated from higher memory to lower memory. From bottom to top, the first 144 megabytes is reserved for the big geek devices. The next 112 megabytes to 256 megabytes is reserved for the legacy devices, including the serial and the RTC. The memory from 256 megabytes to 1 gigabyte is the first part of the PCI MMIO space, where the PCI devices which only support 32-bit addressing are allocated. The first 256 megabytes memory from 1 gigabyte to 2 gigabyte is for the PCI MM config, and the rest is reserved for the future use. Memory from 2 gigabyte to the physical address end is for DRAM and the second part of the PCI MMIO devices. Since we allocate device from higher to lower, the DRAM has a dynamic size which depends on the number of high-mem PCI MMIO devices. In this slide, I'm going to introduce the ARC64 specific implementations that we added to the CloudHypervisor. Code bases from this part were originally from the Firecracker project. We did modifications to these code bases to fit the own requirements of the CloudHypervisor project. The first part of the ARC64 specific implementations is the ARC64 registers. And this part is based on the KVM binding script from Rust VMM. Similarly as the Linux kernel, we divided the ARC64 registers into two parts, namely the core registers and the system registers. Key devices for the ARC64 are the VGig device that manages the interrupt and the RTC device that provides clock. The implementation of VGig devices are based on the KVM I/O controls. GigV2, GigV3, and GigV3 ITS were implemented respectively. The RTC device is implemented through software emulation. The VM snapshot restore feature on ARM has been merged to the master branch recently. It is based on the existing implementations of x86, with some modifications to fit the ARM platform. The snapshot or the restore process can be separately summarized into a single figure, where the orange part is the step needed on the x86 platform. The blue part is the step needed on the ARM platform, and the black part is the common step for both platforms. In order to save the states of the VM, we need to save each component of the the VM in a specific order. In current implementation, we save the states following the order of CPU manager, memory manager, and device manager. On AX64 platform, the CPU states that needed to be saved are the core registers, system registers, KVM MP state, and the MPIDR register, which are different from those for the x86 platform. Also, a crucial step of saving the VM on AX64 platform is saving the states of the VGig device, namely saving the distributor, redistributor, and ICC registers, as well as the GigD control R register. This step should be executed between saving the memory manager and saving the device manager. The VM restore follows the order of memory manager, CPU manager, and device manager. One thing that needs to be noticed is that previously at the step of restoring the CPU manager, the vCPUs are started directly after their states are restored. However, on AX64, the VGig is required to be created and restored before the vCPUs are started. Therefore, the original design was refactored. The start of the vCPUs was split into a single step. The restoring of the VGig was inserted before vCPUs are started. So, the previous slides has summarized the work we have done so far. Future works on ARM platform include some code redesign and feature parity on AX64. Currently, the code to generate FDT is based on the Rust foreign function interface, which depends on a C library. Calling a Rust FFI for C functions needs Rust unsafe blocks, which is not preferred. To address this problem, both the CloudHypervisor and the Rust VMM community have suggested that we could probably implement a dedicated FDT create in Rust, and any design comments are highly welcome to the GitHub issue. The feature parity on AX64 contains the improvement of the VM snapshot restore support, namely the save restore for the GigV3 ITS, as well as some other features such as ACPI, UEFI, VFIO, and CPU device hot plug support. Now I'm going to do some demos about the basic use of CloudHypervisor and VM snapshot restore using CloudHypervisor. Here we open a terminal. This machine has a Ubuntu Bionic OS pre-installed. In this demo, we assume that the essential packages, including Git, build essentials, and libfdt, as well as the Rust toolchains, have already installed on this machine. The current stable release of Rust toolchains would be enough for this demo. Before this demo, I have prepared the kernel and disk image file for the guest VM. Here for the guest VM, we use the Ubuntu full call. In the beginning, we firstly verify the machine architecture using uname-m. Now we can see that we are on the AX64 host. The next step is getting the CloudHypervisor source code. Here, we clone the current master branch of CloudHypervisor. Next, we go to the source code directory and build the source code using cargo. Here we build the current master branch. We use KVM for this demo. Now the code is building. It will take about 1 minute to build this binary. The CloudHypervisor binary will be placed in target debug directory. After the binary is built, here we can start the guest VM. Here, I will give a brief introduction to the command we will use. The API socket option here is to tell the CloudHypervisor to create a socket file for other process to connect. The kernel option provides the kernel, and the disk option provides the disk file for the guest VM. The command line option passes the command line to the guest kernel. The CPU option and the memory option determines the guest vCPUs and memory size. Now we run this command. We can see that our guest VM has been started. After the guest VM has been started, we can log into this guest VM and verify the number of vCPUs and the size of memory. We can see that the CPU number is 2, which is correct. Also, we can verify the memory size, which is also correct. In order to take a snapshot of this VM, we need to open a new terminal. Here we will use the chremote binary as a tool to connect to the socket file we have just created. It's here. And we can also send command through the socket to the CloudHypervisor API server. To take a snapshot, firstly, we need to pause the VM. Now we can see that the VM has been paused. Now we make a directory to store the snapshot data. Next, we take a snapshot of this VM. After all of this, we can resume this VM. Now we can see that the VM has been resumed. We can here power off this VM. To restore the VM using the snapshot file we have just created, we firstly start the CloudHypervisor API server and store the VM from these files. Now we go to our second terminal and resume this VM. Now we can see that the VM has been resumed, and this is the exact VM we have just powered off. Thanks for the watching.